warm-up, we discussed about a line. And the unit of this topic is linearization. So it would make sense that we're going back and looking at vocabulary about a line. So it says a line passes through the point 2,5 and has a slope 0.42. Write the equation of the line. So that's basic algebra. Being able to fill in m and use y2 and x2 to fill in point slope 4. So you get y equals 0.42, parentheses x minus 2, and you can add that 5 or have y minus 5 to start. What is the y value when x equals 0.23, or 2.3 rather? So you would take 2.3, you could plug it in here, you could plug it in there, anywhere you want, and get 5.126. And then the question was, how much does y change when x changes? So y originally was at 5. Y changes to 5.126. Therefore, y changes by 0.126. That change in y is divided by that 0.3, which is 0.42. So again, delta y represents change in y, delta x represents change in x. So delta y is equal to 0.42 times delta x. So that's where you get the 0.42 times 0.3. You can also get it by subtracting between the two numbers. So again, like I said, we're taking everything we used to know and adding or subtracting it sort of into this new realm of calculus. So what's the point of a tangent line? We've been talking about tangent lines since September, and now you're going to finally understand why the tangent line, what does it represent, and where does it belong? Well, it's a useful representation of a curve. If you get closer and closer and closer and closer to a point of tangency, then we should notice that that point of tangency becomes linear. So for example, if you took a quadratic equation on your calculator and you zoomed in and zoomed in and zoomed in using that zoom box feature, as you continued to zoom into that quadratic, it would eventually become linear looking. Linearization says a couple things about differentiability and functions. So linearization says that if f is differentiable at x equals a, then the equation of the tangent line L of x is equal to f of a plus f prime a times x minus a. Guys, that's just point slope form. I even show you that rewritten down below. A tangent line is an approximation of a delta y at a new value of x. The tangent line is an approximation of delta y at a new value of x. That is the purpose of linearization, to approximate a change in y at a new value of x. My friends in the back who are getting blocked by heads. So as we were working on our mins and max, we talked about concavity and increasing and decreasing, and we have been focusing a lot on their effects. So what we're going to talk a little about even more today is how linearization's concavity affects tangent lines. Are we okay for me to switch slides? So tangent lines and concavity go hand in hand. We've been talking a ton about increase and decrease, concave up, concave down, and extrema. That has been our primary focus over the past few weeks. So now we're going to talk about what if we can't find exact points? Well, if a graph is concave up and increasing, our tangent line is going to give an underestimate of that approximate linearization. So linearization allows us to approximate a value on the original function without knowing what it is. But it's always either going to be an over or an underestimate of what that original value is. Concavity with tangency allows me to know which category it falls into. So if graphs are concave up, then we have underestimates. If graphs are concave down, we have overestimates. So the estimation of a local linearization is either going to be an under or an over based on the concavity of the graph. So you can think of up as under, so the U's sort of go together. Concave down is over, so if something's concave down, you jump over it. So it's an overestimate, because if it's concave down, you're going over. If it's going up, you're going to be under it. So if like you're crawling underneath something concave up, you'd go under. So it says, find the equation of the tangent line for f of x. We know how to find equations of tangent lines. We've been doing that forever. So let's go ahead and do that again now. So f of x is the square root of x. So in order to find the equation of the tangent line at x equals 4, I need to know what is f prime of x at x equals 4. So f prime of x is 1/2 x to the negative 1/2. F prime of 4 would be 1/2 square roots of 4, or 1/2 times 2, which is 1/4. So the equation of my tangent line would be y minus y2, which is 2, given to me in the problem, 1/4 x minus 4. So nothing is new about the tangent line. What we're adding is this approximation aspect. So we want to find the equation of the tangent line now at the point 4.2, or 4.1 rather. So I want you to approximate f of 4.1. And obviously I don't expect you to know what the square root of 4.1 is. That's not something you should easily know. It's something you could do on a calculator, but you were to assume this is a non-calculator problem. So where this new aspect is coming into play is that we can approximate f of 4.1 by using the tangent line. So what I'm going to do is plug 4.1 into x in the equation of my tangent line. So I get y minus 2 equals 1/4, 4.1 minus 4, minus 4 is 0.1, which is also the same as 1/10. Well, 1/10 times 1/4, really? 1/10 times 1/4 is 1/40th. Adding 2 to the other side, we get 2 and 1/40th. Which 1/40th is 0.025 because 1/4 is 0.25. So 1/40th is 0.025. That's like 1/400th would be 0.0025. And so on and so forth. So the square root of 4.1 using linear approximation is 2.025. Is a square root function concave up or concave down? So if you were to think about the original square root, do you consider that graph concave up or concave down? What? Yeah, it's increasing concave down. So an increasing concave down tells me that my approximation is an overestimate. So remember, our point was 4.2. So my tangent line is here. And my approximation is on my tangent line at this point right there. So you could see how that little tiny red dot would be above the graph, thus making that an overestimate. You could use your calculator and find the actual value of 4.1. So the square root of 4.1 on a calculator is 2.0248. So would you say our approximation of 2.025 is a pretty good approximation? So now, somebody ever asks you to find the square root of a number, you could do it using calculus. So if you ever needed to find the square root on any sort of test without a calculator, you could do it using calc. I know that makes you so happy. Okay. So on this screen, what I did was actually graph those on Desmos to show you like the actual square root and the equation of the tangent line, so you could see that overestimate in action. We already did that. All right. Find the linearization. So sometimes you're going to see linearization represented as L of x. You're going to see L of x instead of the tangent line equation. So L of x is essentially our tangent line equation, where L of x is equal to that f of a form plus f prime a times x minus a, where really a just represents the point, f prime of a represents our slope, and f of a represents the y value at our point. So it says final linearization of f of x equals the natural log of x plus 1. So right away, after I see an f of x, I know I need an f prime of x. So f prime of x is the derivative of the natural log. So hopefully we haven't forgotten our derivatives, because it seems like it's been a while since we did anything that was non-polynomial. So derivative of ln x is 1 over the inside times derivative of the inside, which in this case is 1. And we want to find that at x equals 0. So that x equals 0, that's my a. So I'm looking for f prime of 0 and f of 0. So that 0 is my a. In this case, a is equal to 0. So f prime of 0 is 1 over 1, which is 1. F of 0 is the natural log of 0 plus 1, which is the natural log of 1. And we know that the natural log of 1 is zero. Okay, so natural log of 1 is 0. Therefore, my L of x equation is f of a, which is 0, plus f prime a, which is 1, times x minus a, which is 0. We're asked to approximate f of 0.1. So L of 0.1 would be equal to 0, which is gone, 1 times 0.1 or we see that the linearization approximation of the natural log at 0.1 is 0.1. So the actual would be f of 0.1, which would be the natural log of 1 plus 0.1, which is 0.0953. So again, this is the actual. This is my linear approximation. So is my linear approximation an over or an under? It's an over. So what does that tell you about the natural log function? My approximation is an overestimate. The natural log is concave down. So this also is a way to tell you about the shape of the graph. Since my approximation is an overestimate, f of x is concave down. Okay. Use linearization to approximate the square root and the cube root of 123. They may not tell you anything beyond this. It is your job to determine what is the function, what value is close to that function that I can use to approximate it, and then what is the approximation. So let's start with the 123. And the square root function. So if I'm trying to approximate the square root of 123, that tells me that my f of x is the square root of x. If f of x is the square root of x, and I'm trying to approximate 123, I need a value of x that I could find easily near 123. So I need an a value to plug in so that I can find f of a and f prime of a easily with a square root. What do you think, Maddie? Perfect. So I'm going to use my x value to be 121 so that my y value is a nice 11. So 11 is my f of a and 121 is my a. So my L of x is f of a plus f prime of a times x minus a. So what am I missing still for linearization? I need f prime of a. So f prime of x is 1/2 x to the negative 1/2. F prime of 121 is 1/2 121 to the negative 1/2. So the square root of 121 is 11. 1/2 times 11 is 1/22. So that means my linear approximation equation is 11 plus 122 over or times x minus 121. And now I can use that to approximate 123. So 123 minus 121 is 2. 2 times 1/22 is 1/11. So you get 11 and 1/11 for your approximation. 1/11 is actually one of those weird repeating decimals. So 1/11 is actually 0.09 repeating. Would a square root function be concave up or concave down? Ready to discuss this? Square root is concave down. Therefore, this is an overestimate. In order to do the cubic, you would have to do this all over again with a new f of x, because now my f of x is the cube root of x, which means I need a new f of a, because the cube root of 121 would not be a nice number. However, the cube root of what number would be? What would be a nice cube root near 123, Maddie? Yeah, 125 and 5. So then you'd find your derivative of the cube root. So again, that'd be 1/3 x, and then 1/3 minus 1 is the negative 2/3. So f prime of 125 would be 1 over 3. 125, I'd take it to the cube root and then square it so that your numbers are easier to see. So the cube root would be 5. 5 squared would be 25. 25 times 3 would be 175. So that my L of x became 5 plus 175, x minus 125. So I got 5 plus 175, 123 minus 125, or 5 minus 2/75. So we're going to end with linear approximation here for today. There's a couple problems we're going to do in the textbook to try this on our own. They're going to be very similar to the questions we looked at here. Tomorrow you're going to be on AP Classroom, reviewing kind of everything we've done. There will be some multiple choice, and then I have to see if I like everything out there. If not, there might be like maybe 5 on there and a couple on Delta. I will let you know tomorrow where I kind of have you standing with your review questions. We are starting to wrap up Chapter 4, and Chapter 5 takes us into the new segment. So we have one more unit for Chapter 4, and then we'll be done. So I'm thinking probably chapter test maybe like mid next week. Your mock exam in here is March 25th. So, and then pretty much after mock exam, we're going to try to wrap things up so that we have the month of April to review. We're running down to the nitty-gritty for getting to that AP exam.